Welcome. In this video I'm going to show you how you can perform a Freeman-Tukey-Read test of goodness of fit with Microsoft Excel. I'm going to focus on how to obtain the output, not so much if you should be using this test, because there are quite a lot of variations of this test or alternatives. This test is actually not a single test, it's actually a whole range of tests because you can set certain weights yourself. The fastest way of doing this with Excel would actually be to simply install my add-in, and then I have one function that can do it all. But if you don't want to use my library or my add-in, then this is the video to watch. To show you how it can be done, I have some data. It was taken from the General Social Survey from 2012. I adjusted that data sometimes for examples, but it serves a nice purpose. The first thing we need is the number of categories. So in this case there were 5 categories for this field. These were actually married, divorced, separated, never married, and widowed. We should also set the weights. You can have as many weights as you like, but they should sum up to 4. So I'm using what is usually the default for this test, 4/3 and 8/3, and as you can see the sum is indeed 4. Next up, we determine the frequencies, the counts for each of those categories. So we can use COUNTIF for that, give it the range, and then the criteria. I'm using a semicolon just to separate the parameters. Your system might simply use a comma. After the first one, you can simply copy paste it down, and of course we also like to see the total, which is simply the sum of those frequencies. We need to set the expected counts. If you already have some certain expected counts, you can just fill them out. Otherwise, what's quite often done is that you would assume that each of these would have the same frequency in the population. So that simply would mean if there would be 1941, you divide it over the number of categories, which is that 5. So then each category would have expected 388.2. Now for that test statistic, that's the longest calculation. This is most of the formula. As you can see, it starts with taking the square root of both those frequencies and those expected counts, subtract the 2 and square the results. That's those. So I've done that over here. It simply uses the square root function minus the other square root and square the result, which is done with this. I think it's called a radical sign, and you can copy paste that first one then down. This part is slightly trickier because it goes for each weight. So the BJ is simply the weight. So the first one is this one and the second one is that one. We multiply that with the square root of the ratio of the frequencies and the expected counts. And each of those gets raised to whichever weight we're using minus 1. So for the first weight, that will give us all of this. So it's taking the first weight, multiplies it with the square root of that ratio, and then raising it to that same weight number, minus 1. Now luckily I only have 2, so for the second one, as you can see, it's using the similar formula, but then it's using the second weight. After that, we multiply, of course, we sum those all up. So this column over here, this I column, has all of this in it. We need to multiply that with the first result, so that's what's being done over here. Then we only still need to sum all of these up, and then we have our chi-square value. So that's simply the sum of the results of the previous step. We also need the degrees of freedom, which is simply the number of categories that we saw earlier. The 5 minus 1 gives us, in this case, nicely 4. Now to use the chi-square distribution, to find the p-value, we can simply use the newer function dist, right tail, give it the chi-square value and the degrees of freedom, and we should get ourselves a result. The e minus 251 means that we need to multiply this 4.3868 with 1 over 10 to the power of 251, which simply means there's going to be 0 point and then 250 zeros or something, and then 43868. So extremely small, smaller than the usual threshold of 0.05. So we would reject the assumption, and in this case the assumption would be that all the expected counts would have been the same, or that the frequencies would have been the same in the population, so they're significantly different. You could also apply some corrections. There is a so-called Yates correction. The formula for that differs a little bit sometimes, but in essence what it usually boils down to is this. If the observed count is greater than the expected count, you subtract a half, otherwise you add a half. So these were my observed counts, these were the expected counts, or just simply reference, and if this one, then I just use some if statements to actually incorporate all of this. Then you can repeat all the steps from earlier, but then instead of using the regular frequencies, you use these adjusted frequencies. There's also a E.S. Pearson correction, which is simply to take the original chi-square value and multiply it with the sample size minus 1 divided over that sample size. So, and then you get the result slightly different. The Williams correction, slightly different again. You take the number of categories, add 1, and divide it over 6 times the sample size. So, and you add 1 to all of that. Then, in this case, you don't multiply the original chi-square value, but you divide it by this factor, and you get yourself the adjusted chi-square value. Alright, and that was it. I hope this video was helpful, and I thank you for watching.